Good afternoon, everyone, and thank you for joining us this afternoon for our webinar on a holistic approach to high-integrity die casting. As you can see from Martin Hartley's bio, he has spent a good part of his career involved with development of new applications for structural high-integrity castings. We have worked with Martin since early in his career when he was sales and marketing manager for Alcan's BDW operation in Marktschwaben, Germany. BDW was involved in developing the B-pillar and A-pillars for the Audi A2, the shock tower for BMW, and many other of the earliest structural castings which were both heat-treatable and weldable. Martin has a wealth of knowledge to share with you on this subject. We are privileged to have Martin conduct this webinar for us today. If you log any of your questions that you might have during the presentation, we'll try to address them at the end of Martin's presentation. So it's all yours, Martin.
Okay, so let's get started. So the session is called High Integrity Die Casting, a holistic approach to improve die casting quality. We thought we'd call it like that because many times I was asked, is there one patent that covers structural die casting or high integrity die when we used to sell high Q cast, and actually not one patent. You could not file one patent covering how to do it. It's as the title here says, it's really a holistic approach, just doing using the right alloys, the right processes, and doing everything the right way. So we're going to cover in this session the aluminum content in automotive, which represents the opportunity for die casters. Then the requirements for high integrity die casting, the success factors. We go into a little more details about alloys and tempers, heat treatments, and then the products and services that we offer for you, and we'll finish up with a summary and questions and answers. So why would you invest in aluminum die casting technologies? Well, first of all, the aluminum use in automotive is continuing to grow, and actually quite significantly. That's done to reduce weight and improve fuel economy. It has been stated in the press many times, 6.5% reduction in fuel consumption can be achieved for every 10% reduction in mass, and at the same time you reduce emissions. There's a lot of political or regulatory as well as social and consumer pressure all over the world. In North America, I'm sure everybody has heard about the CAFE standards that regulate the corporate average fuel economy. And the only way to get there is, well, to get the weight down, among other things, of course. Now, high-pressure die castings offer a lot of advantages over other processes if the right technologies and alloys are applied, because, as you all know, we can offer very thin wall, very intricate parts, large surface, very high freezing rate, which gives a very good grain structure. So in theory, we have all the right ingredients to produce wonderful structural parts. So let's see what we need to do to get there. Before we start with the technical content, I'm sure most of you have seen the famous Ducker studies, and Dick Schultz put them together and showed that right now we're at about 343 pounds per light vehicle in North America, and that is supposed to grow to about 400 pounds by 2015. And if we look out a little further, by 2025, we're supposed to hit 550 pounds per light vehicle. Now, we've gone up there, as you can see, in kind of waves. First, the heat exchangers switched from copper to aluminum, and then the wheels were attacked, because wheels, of course, are an ideal target for weight reduction. They're both unsprung and rotating mass. And then the heads and blocks, the engine was attacked because that of course brings the big imbalance in a car because it sits in the front usually. Right now we see a big trend with hoods being added to that, but the big untapped potential really is in the body in white, the car body structure itself, as well as in doors and other closures. Most of the high-pressure die castings so far are concentrated in 3 vehicle systems. We know them very well: the transmissions and driveline, big transmission cases, etc. Then, of course, the engine itself with engine blocks and smaller parts like oil pans on the head covers and so on, and to some extent in heat exchangers. Now, the future grows. Really, we expect that all to happen in the body structure because, well, the other things are either already maxed out or we actually will see certain downsizing, especially when it comes to engines. So new applications like heat-treatable structural aluminum parts will actually see the largest growth in the market. That will mainly be in automotive, but we will also see it in other industries like in motorbikes or recreational vehicles. Those parts are definitely higher value added and hopefully also higher margin, and they will offer a clear competitive distinction for any die caster. Usually OEMs are looking for die casters rather close by and certainly not offshore. This is already a substantial growth opportunity that's happening in Europe, to some extent Japan as well, and we clearly see it coming over to North America. This picture from Shiloh just shows a little bit the different parts that can be made in high pressure die casting in the car body structure. I think most of you are familiar with the shock tower that originally Contec made for the BMW X5, and then Albany, Chicago took that over, which is now Shiloh. Then we have A pillars, B pillars, all sorts of brackets or nodes for the space frame, inner door panels, and so on. All these structural castings are used for replacing typically heavier materials, often steel, but also aluminum assemblies, often stampings, or any high-cost materials and processes. Very often weldments, and they're used to get lower weight because you can get thinner walls with die casting than with any other casting process, which will lead to increased fuel economy. You get performance increases. That's especially true when it comes to fatigue because the high freezing rate and the skin effect of die castings can hardly be beat by other casting processes. It's also used for pressure-tight hydraulics and other components that we will see in just a minute. Now, just 2 examples of part integration. If we look at the Audi A8, the first Audi A8 B-pillar, which was made out of 8 different components, die-cast part, extrusions, and sheet, with a total of over 9 pounds. And 6 years later in production was the Audi A2 B-pillar, 1 single part, same size, but only 5 pounds, and it was 1 high-integrity, high-pressure die casting. Another example that most of you, I'm sure, know is the BMW X5 shock tower, and there the original version was actually 5 welded steel stampings. You can't compare it one-to-one, but overall you can say that if a similar part had to be made in steel, it would be certainly a lot heavier, and we think it's about 40% of weight saving that you can typically get by switching to structural die casting made in aluminum. It typically starts out in really high-end vehicles, and some of you probably remember earlier presentations from Daimler were on the SLS, the AMG supercar roadster, and in the meantime, here's the example of the regular SL roadster, but most of you probably already heard that it has now gone all the way down even to the C-Class, and the next C-Class that's launched, I believe next year, will have 7 or 8 structural die castings made by Bocar in Mexico. So if we look at the body structure here, we see it's of course not going to be just die castings, it's going to be a mix, but the SL has actually 44% of the car body structure made out of castings, most of them die castings. The rest is aluminum extrusion profiles and some sheet material, stamped sheet, where you need really high strength. You do need high strength steel and a few other materials. Now if you look at the castings, as I said, the majority is structural die castings. We have 34 high vacuum, high pressure die casting parts here in red, and in orange you can see 2 low pressure die cast parts. Those are very big and very complicated with internal cores. The total weight of the castings is 110 kilos, and interestingly enough, the weight saving over a traditional steel car body with this aluminum body was also about 110 kilos. Here is one example that wasn't covered before. That is the firewall, an interesting part, and you can see the dimension is huge, of course, going all across the car. The weight 7 kilos, so about 15 pounds, integrated 6 different parts, and that really helped reaching the rigidity goals in that roadster. Other current and potential applications that we're looking at is in the suspension area. Of course, in the underbody already we have a lot of cross members and engine cradles, things like that. But if there are thin-walled suspension parts, then they can also be made in high-integrity die casting. And if it's outside of the automotive sector, then one example here is the Yamaha motorbike main and seat frame. They are both made in Japan in the silicon 36 alloy. Or this part, this is actually made by AMT in Quebec. They are producing this in originally silicon 36, now Oral 2, and it's a suspension part for the BRP skidoos, and that replaced 2 gravity cast parts, which were of course a lot thicker, and therefore they reduced the weight and machining costs. So what are the requirements for high-integrity aluminum die castings? Well, first of all, of course, weight reduction, because as mentioned before, we can cast very thin with high precision. We do want to integrate parts, because that is not just helping to save weight, but also to save costs. Otherwise, you have to use complicated and expensive joining processes, often welding. High mechanical properties, and here is just one example that I've taken from the Mercedes specification. Now, what is interesting to see is the strength targets aren't that challenging. You could reach that with an A380 die casting. The tricky thing is really how do I get 10% and more elongation that is necessary for the crash behavior, or in order to be able to rivet the part. Now, of course, we all know that crash behavior in a high-speed impact can't really be measured with a very low-speed tensile test. So therefore, at least a certain bending test, which is very common with sheet applications, is typically used here, but ideally OEMs do real crash test with these parts. So crash performance is of course a big requirement. Then of course corrosion resistance in the car body structure. Very often they have to be weldable and they have to be heat treatable, and anyone who has put a die casting into a heat treatment furnace knows that the big challenge here is blisters. Then that leads to surface defects, but the surface quality in general is a big requirement, especially in the joining or contact surfaces. The parts have to be distortion-free with very tight tolerances. That is one reason why we don't want to do die casting for these parts. Some have to be pressure tight, etc. Now, when we look at crash relevant parts, another example outside of the automotive sector is here from Mercury Marine. And what they do is basically their kind of crash test is called a log test, which means they have to drive a boat over a log in a river, and the engine has to survive and not swing into the inside of the boat and kill people. So traditionally, high iron, their so-called XK60 360 alloy was used, and they could just barely pass a 30 miles per hour log test. And by developing and then switching to their proprietary Mercalloy 367 in this case, they actually managed to save this casting beyond the log test. It did not split completely, not break completely, and this is actually now after a 60 miles per hour log test. So a huge improvement in terms of crash performance. So what are the typical die casting defects? Why do we get kind of lousy properties in standard die casting when it comes to elongation and crash performance? Well, first of all, we all know gas porosity, and that can come from many different factors. It can be the hydrogen in the metal. It can be gas inclusions during turbulent filling. It can come from the lubricant, from many sources. Shrinkage porosity, we all know that. When we try to feed a thicker section through a thinner section, or anytime we have a thicker section, we risk that. Then of course oxide inclusions, which will often lead to shrinkage porosity because that's where the materials just don't bond together anymore. These oxide inclusions simply come whenever the oxide surface from the melt was folded over, and these folded oxide films got washed into our melt and then end up in the part. And then of course sludge particles, and I'll get back on the sludge particles a little later. They are intermetallic compounds, mainly iron, manganese, sometimes chrome in there, and they will be stress risers later on and lead to failure of the parts. So what are the factors affecting die casting quality? We have to start with alloy. So it's all about alloy composition and the impurities in the chemistry. The metal quality, and here we talk about oxides, so how we treat the metal. Hydrogen content. Hydrogen is the only gas that's soluble in liquid aluminum, but not when it's frozen. So if we have any hydrogen in our melt, later on it will end up as bubbles. Then the already mentioned sludge, dross, and all sorts of other inclusions. The metal temperature shouldn't be too high and certainly not too low. The metal treatment, the transfer, and ultimately the delivery to the shot sleeve. Then the die casting machine, which size, type, equipment, clamp platen, the shot end, pressure, closed loop control, and so on. The monitoring and control system of the die casting machine for all critical process parameters, full machine diagnostic, And of course, ideally, we want to have a graphical user interface and provide SPC data. The shot tooling, cold chamber, we want to have proper size, internal temperature control, etc. The shot tip, plunger loop, the type and its application. And the die casting dies, gating design, overflow design, and we'll talk a lot more about that. The part design itself, wall thicknesses and changes, as mentioned before. The die temperature, the lubricant type and application and its efficiency. The vacuum system, which type, which level, how much cavity pressure is acceptable, how do I control it. Part extraction and quench system. And of course the trimming and heat treatment and any other subsequent process steps. So standard die castings are sometimes described as two sound skins around foam. And when we look at this part, whenever it gets too thick, we always run into this problem, that we get all sorts of porosity inside, while the skin is actually perfectly sound, and even the body is pretty good. Therefore, what we want to apply is vacuum, and not just standard vacuum, but really high vacuum. And it's of course not just about the vacuum, it's also about doing, as mentioned before, everything else right. So what are the success factors? As mentioned before, it's a holistic approach. You have to do everything right, start with right die design, do the simulation, right gating system, use the right chemistry, use the right melt treatment, vacuum, lubricants, the chemistry, the application, how much, humidity monitoring, and so on. So you have to go through the entire process chain. And we'll actually have a little bit of a look into the process chain in the next couple of slides. I can't go into all the details because I have probably 2-3 hours of presentation material on every single block here, but at least we get a little bit of a glance into this. High quality alloys, we move that to the back. We'll come back to this later on. We'll start off with melting and melt treatment, and typically then we do a composition check and adjustment, proper melt treatment and transfer, do a density check, then the high integrity casting and trimming itself. After that, depending on the requirements, you might see X-ray validability, crack inspection, and then I say here low distortion heat treatment, because these very large surface, thin-walled, dangly parts, they distort pretty well when you put them into a typical water quench. So you have to work with precision air quench when you come out of the solution heat treatment. After that, you have your properties. So you do your tensile test or bending test. You do a blister check, because heat treatment is also a very good testing method to see how sound your casting quality is. Any bubbles will now have blistered up. Then you might have to do some straightening. Then size tolerance check, dimensional check after machining, and then it usually gets sent out, and any surface coating is typically done right before the parts get assembled. Now, if we start looking at melting, melt treatment, and transfer, what we want to pay attention to is oxides. Any aluminum, especially when it's liquid, will build an oxide film very quickly on the surface, and that is fine as long as we don't fold the oxide layer into our part. So this is something we have to avoid. Hydrogen, as I said, hydrogen is the only gas that's soluble in liquid aluminum, but will then bubble out as soon as the metal freezes. Sludge is a big problem, and most of you are probably familiar with the sludge factor. It's 1 times iron plus 2 times the manganese plus 3 times chromium. I mention that here because when we talk about high integrity die castings, we lower the iron content. As we've seen before, typical die casting alloys 1.3% iron. So you can already see that gets you pretty high on that curve here in terms of sludge factor, plus 2 times the manganese. And for high integrity die castings, we actually replace iron with manganese. So manganese is twice as harmful for our sludge factor as iron is, and therefore we have to really watch out with our chemistry so we don't create a big sludge problem. Then of course dross and any other inclusions that come from our melting and melt transfer stream. So what we need to do is proper temperature control of the melt. Never overheat it and don't let it go too low because otherwise we get into the sludge problem. Avoid any excessive turbulences and absolutely avoid splashing. Splashing always means I fold in the oxide layer. Do proper degassing, fluxing, filtering, and settling. Very often people think that if I can't fill my die, I just need to increase my melt temperature. And yes, that helps, but sometimes actually looking at a filter helps a lot more. If we look at filtered metal versus unfiltered metal, the filter is actually worth 100 degrees C, so over 200 degrees F. So that would do really wonders if I don't have to overheat my metal that much. If we talk about degassing, that is removal of the hydrogen from molten aluminum, and this is typically done with nitrogen or argon. Ideally, you do want to do rotary degassing, and you could either then inject fluxing directly with the nitrogen or argon, or you do it on the surface. But fluxing here in this case is used to remove the dirt, so the dirt actually sticks either to the bubbles coming up or to the surface. Now any waterfall is really bad. Here worst case example. So that melt is definitely going to be full of oxide films. But very often I see that even very good die casters do everything right, and they filtered the metal and they degassed and fluxed and cleaned it up, but then they still end up with oxide problems because in the transfer into their dosing furnace, they have to lift the transfer crucible high up, and then you get 3 feet waterfall coming from the transfer crucible into the dosing furnace. So here again, this can cause problems. Now when we talk about dosing, typically in die casting we use ladles. For high integrity die casting, there are ways to get there with ladles, but I would recommend using a dosing furnace. It helps in 2 ways. One is it really helps getting a low turbulent flow of the metal into the shot sleeve, and B, my melt quality is definitely going to be better because I can continuously degas. I can very often still filter inside the holding furnace or on the bottom of the pump. Plus I actually have an enclosed system, so I don't lose heat, and therefore I can keep the melt temperature a little lower. Plus I actually have an inert atmosphere on top, so I will get less oxidation on the metal surface as well. BDW actually went even further, and they said we need to get rid of all the oxides before we get the metal into the shot sleeve, and they developed their own little, what they call a swivel launder, and this is a simple launder that actually moves downward and puts the metal nicely on the bottom of the shot sleeve, which eliminates, of course, all the turbulence that you would get, but B, also helped extend the life of the shot sleeve by a factor of about 10. And when you use basically primary structural alloys, that really goes a long way because they are very aggressive both on the dies and on the shot sleeve. So now before we can get started with making a die and actually casting anything, we need to design the part, and therefore we need simulation. So we need to have a proper simulation program. There are many out there, but make sure you get material data in there, all the process parameters, and of course the part and gating design. And the simulation has to be used to optimize the runner design, provide a continuous flow path, a homogeneous one flow into and through the entire part. Don't forget to optimize the overflow as well, including the vacuum valve and position, utilization of gates along nearly the entire front edge of the part, and we will see a few pictures of that in just a minute. It helps us predict casting defects, temperature distribution at the surface of the cavity, the velocity field in the liquid metal, and it should help us get a homogeneous metal front all the way through the part. We see here an example of a gating system. Some people call it the antler gating design because it looks a bit like that, but you can see the metal goes in over the entire front of the part. So with the simulation, you optimize your metal flows. Here in this case, in the first simulation we saw we had a metal front coming in here and another metal front coming in here, and these two metal fronts would come together and lock in air and dirt, because any metal front will push ahead all the dirt that's left in the cavity. That's why we want a homogeneous flow all the way through and push all the dirt into the overflows. That is also why you typically will find better properties on the inlet side than on the outlet side. Now when we talk about that, heating cooling channels of these thin wall structural parts, very different to typical thick wall, let's say engine blocks or transmission cases where we shoot an awful lot of metal into this die. Here the typical wall thickness is just 2-3 millimeters, so there is very little heat coming into the die from the metal. Therefore, it's not so much about cooling the die down, it's more about heating the die to a homogeneous and to the desired temperature, and controlling that. And if you have hot spots, you would rather use jet cooling than a lot of big cooling channels. Now here in this picture we also see the plunger and then in-gates, and again this so-called antler design. Another beauty we see here, these dots are actually the ejector pins, so you can see with this design that helps us to also put the ejector pins actually on the in-gates, not on the part, which is very helpful. And then we see on the other side the overflows, and here the vacuum valves. Talking about vacuum, of course we are using very high vacuum here, so sealing of the die is very important, and sealing every part of the process that could suck air from the outside in, which means of course also the shot chamber. Then the product development, we need a component design that is really robust, meets both functional and manufacturing requirements. That will lead to higher quality products, and it's very important that design engineers work together with the casting engineers from the early stages of the product development, and that you include the gating and die design. Simulation, as mentioned, is a must. The gating design is extremely important, but you shouldn't overlook the vacuum gating. That is very important too. Now when we have the process set up and we have our die, now we have to make sure the process works. So we need advanced process controls and monitoring system, ideally a real-time adjustable control system, closed loop. So shot control in order to reduce air entrapment during the shot phase. I got a few more slides on that in just a minute. A smooth metal flow and flexibility of adjustment during the fast shot, the fill phase. Repeatability, deceleration for low impact so we don't get massive flashing. Whenever we have flashes build up, we also know that that is stressing our dies and it's squeezing the dies apart. So our vacuum will suffer from that. And of course, programmability, very important. Then the vacuum monitoring and control system. You want to be able to see your shot profile and your vacuum curve on one screen. You want to apply the vacuum during the fast shot. Again, repeatability is really key because, of course, your fast shot is only milliseconds. Detecting leaks or blockage is very important. Your control system needs to be able to tell you immediately if a part was made and the vacuum system was blocked or was leaking. And then it needs to help you troubleshoot quickly. It also needs to control other die cavity sensors and any other sensors like, for example, the mentioned TTV. So you want to monitor all the key variables, shot end hydraulics, position, velocity, pressure, the vacuum as mentioned. Derive key process parameters. You also want to control your furnace, metal and die temperatures, tie bar stress, cycle times, etc. So all of this needs to be reported by the monitoring equipment, and of course it should tell you immediately if a part is out of spec, and if it's not, then you want to have the data stored for later on. So here we see an example of a shot profile monitored with a Visi-Trak real-time shot control system, and that does exactly what we just described before. It's fully programmable control parameters. When we use these monitoring methods, some die casters, I know they use basically just a portable monitoring system. That works, of course, but not for structural die casting. If you want to do high-integrity structural die casting, you need full-time monitoring on every machine 24/7. So you will detect immediately any machine problems, and it tells you where the problem is, and you can find the solution from real data. It will help automatically segregate, suspect, and startup castings. And if you have this permanently installed, of course, then that means you can hide the cabling and sensors and shield them from the environment so they will live a lot longer and need less maintenance. Now if we look at plant-wide monitoring systems, so we have die casting machine 1, 2, whatever you have in the plant, it all feeds the data into network system. It gets backed up automatically. It can be viewed from remote workstations, now even from tablets from home. So you can see at a glance if all your machines are up and running and everything's fine. And very important for structural die casting, it's all stored and every part gets a unique ID, typically a 2D barcode and a human readable code. So basically you're creating like little Swiss watches here, because behind every part you want to record all the history of how it's made, the chemistry, temperatures, speeds, everything. That is basically your life insurance, because with crash sensitive parts, you can't crash them. So you can't really test everything with these parts. So you have to rely on your process. So you want to make sure that all your process parameters were exactly where they're supposed to be. We talked about that slow shot, the fill phase, and I'm sure you are familiar with this. What you want to have is not too slow, like on the left side, where the metal front actually then comes back. Not too fast, where we build a wave and then fold in the oxide layer again and end up, in both cases, with a lot of bubbles in the melt that will end up as porosity in the part. What we want is completely controllable linear ramp up of the slow shot, and therefore a nice metal front running in front of the plunger. Now that is especially important if we look at vacuum die casting, like in structural die casting. Nowadays, very important, we want to have the two-stage vacuum system. We have one vacuum on top of the die, like we've always had, but an additional vacuum line coming into the shot sleeve, so we evacuate from the very beginning. As I mentioned before, at the end of the fast shot, it's very important that we don't get a whole lot of flashes, because the flashes will ruin our die, and especially they will ruin the vacuum. So Visi-Trak offers the so-called soft shot technology that helps decelerate in the end, and hence improve the vacuum and generate less wear and tear on the shot and the clamp and the dies. Now, in order to be able to monitor and control, you first of all need to have proper sensors. Visi-Trak offers this contact-free sensor, and it's mounted either directly here on the rod or on an extra rod, and it's chrome coated and grooved. It's very fine, very precise. You get a very good resolution, and actually the faster the rod moves, the more grooves are passing by the sensor, so the more data points you actually get. So it's a very easy to install and operate system, and proven since over 25 years. It works really well. Now, very important, of course, is if we can monitor it, it's one thing, but the machine needs to be capable of doing precise slow shot speed ramp ups, and then high flow rates for a very fast acceleration and deceleration and all that. So what we need is servo throttling valves, not the older technology, typical binary valves. That is very important, and Visi-Trak offers packages to retrofit existing machines, and there was an article in the Die Casting Engineer not long ago where a case study was shown removing a binary 2 shot valve and the manifold block and replacing it by a two-way Olmsted valve, and it was described what it did, which is very impressive. I can only recommend you can get the article if you want. Just send us an email and we'll send you a copy. Now, of course, you want to be able to see the results of all your monitoring and control efforts immediately. And the latest product we're bringing to the market is the Total Track, the HMI. And now you can really see it on your screen, everything that is going on your die casting machine and around. And it helps you to easily set up and restore any saved jobs. So you basically just type in the part number, and the Total Track takes control, and it pulls out all the saved data, whether it's from the reciprocator, the ladle, anything you want, the entire machine setup. So it helps to quickly change dies and to produce new parts, and you don't have to mess around with programming everything new. And of course, what's very important here is we see all the parameters. It's easily available for the operator or for anybody in the office to look at it. So when we then talk about lubricants, and we mentioned that before, they are a big source of problems in structural die castings. So there are a lot of things to watch out for, but the main thing is never have too much of it, and you need to apply it properly. Both the plunger lubricant and the die lubricant, of course. There isn't just one lubricant that's the best and the only one that works. You will find different technologies and strategies to do that, but it's a very important aspect that needs to be taken into account. Otherwise, it easily destroys your vacuum. Vacuum, we find vacuum die casting very often with anything between 20 and 300 millibar of remaining die pressure. It's used to reduce the cavity gases from the shot sleeve and the die, so we reduce the porosity level and therefore scrap. But very important in structural die casting, we need the vacuum to actually fill these parts with these very thin walls. Otherwise, we could simply not fill such a B-pillar or shock tower. So the high vacuum die casting processes need to be able to actually keep the vacuum level below 50 millibar in the cavity, which means you want to run your system probably down to about 20 millibar to make sure you actually end up with 50 millibar in the cavity. And as I said, you want to have a two-stage vacuum system where you pull vacuum both in the shot sleeve and at the top of your die prior to injection. And keep it during basically the entire shot, at least halfway through your fast shot as well. Monitoring and controlling the vacuum level is key. The main differences that we find is really the vacuum valve type, the control system, and its monitoring approach. So you want to be able to basically put your vacuum curve on top of your shot profile, and depending on how you actuate your valve, your shot control system needs to be able to tell the valve when to close it and when to open it. We typically distinguish between mechanical and hydraulic valves. The mechanical valves, I think everybody's familiar with the typical cast tool or the VDS ProVac or Fonderex valves. The pros are vacuum is pulled through the entire shot. That's ideal. That's what we want. We don't need an expensive controller. It's relatively easy to remove and clean, and biscuit size variation is not an issue. So if your machine is not very precise, then that's a good way to go. The downside is typically smaller valve cross sections and the potential for metal to fill into the valve, and the valves are then also expensive, and it takes quite a bit of maintenance. At BW, we of course had the MF2 system, because MFT is minimum fill time, that was invented by the Turner family, the former owners of BDW. That allows for a much larger cross-sectional area. It does not rely on the metal front to close the valve, so you won't have metal shooting into it as long as your machine is properly under control and your control system tells the vacuum valve when to close exactly. So if you do it right, you will have a lot less downtime. But as I said, it requires a much better control system, and it's more challenging to draw vacuum through the entire fast shot. And it does not account for biscuit size variation. Now, a lot of people say, well, why can't I use my traditional chill vent approach? Well, I guess you could, if you look at the Castvex system from Australia, that is a very interesting approach because, of course, a simple chill vent would be way too small to evacuate enough, but if you increase that area by, let's say, 4 times, so your 80-ton locking force that you require for your chill plate would now actually become a 320-ton locking force. So if you actually need 2 or 3 or 4 of those to evacuate a big die, you can imagine you would need a bloody big machine now. The Australians had this wonderful idea, why don't we just put this in a 3-dimensional shape, and we fold this, and you can see the result is that it's actually basically a valve that is the size of a typical Fondarex valve, but it's the traditional simple chill block technology. So that is in production at Nissan in Australia since over 6 years now, and apparently the result is very good. It brings you the same performance as a mechanical valve, but of course it's not that simple as a technology, because when you look at the valve itself, it is quite complex. It has internal water cooling, built-in air blow to self-clean the washboard. It even has built-in spring-loaded ejector pins, so that makes sure that your part won't stick into the washboard because it's curved, of course. But this is certainly another interesting approach to look at. Now, vacuum and moisture, we know that is certainly not compatible, and a lot of moisture either comes from the air, so make sure the air moisture is low around the die casting machine, but most of it will definitely come from the lubricant. So what you have to make sure is that you use a micro spray and disperse it fine on the surface, and make sure it actually will evaporate before you close the die. And then we had it before, a proper identification of each part when it comes out is important. You can very often see this now on all the structural parts for sure. So it's engraved on every part when the part comes out of the die casting machine, and then the barcode is scanned again for every subsequent process step. So you scan it before you put it into the heat treatment furnace, and then the heat treatment temperature curve is simply added into the data archiver, and anyone who later on scans the 2D code will see all the process parameter through the entire value chain. So this network data archiver is very important. It collects and archives all the data, and then helps to uniquely identify each part. So here you see how it looks like. I had the question a lot, what if the part doesn't have such a surface, or the surface actually gets machined? I have seen people actually putting this on twice. Once after the part comes out of the die casting machine, and then again after machining, because they had to machine this surface. So Visi-Trak is offering all these plant-wide building blocks, starting with the high-speed data acquisition that we saw, including, of course, the precision sensor package, very important, the process monitoring equipment, the shot control, including all the necessary valves and shot control package, then advanced die casting machine control, and finally the plant-wide management solution with remote machine monitoring, quality control, data archiving, and traceability system. So now let's get into alloys and tempers for structural die casting. Those of you who are members of NATCA and get the die casting engineer, I had an article on that subject in the May edition of this year. If you're interested and you would like to get a copy, you can either get it from NATCA or you send me an email. Then you will get a lot more information I can cover in a few minutes here. All these high-integrity die-casting alloys have a few things in common. One of them, they're all low in iron, and I'll show you a few pictures later on what iron actually does. It creates big platelets that destroy our properties. So therefore, typically these alloys replace iron that's used for beating the die soldering with manganese, which does the same job without damaging our properties so much. They all need relatively low copper. How low should be determined in the salt spray test. And they all have strontium additions at different levels for different purposes. Typically, strontium is added only to modify the eutectic silicon. In the case of the Mercalloys, it's also used to beat die soldering. We distinguish between, well, at least two major structural die-casting alloy families. One is the typical one, aluminum silicon alloy family with aluminum plus usually 8 to 12% silicon and up to 0.6% magnesium, then some manganese and a little bit of iron. It was found that up to about 0.22 or even 0.25, the iron is not harmful at the high freezing rate of die casting. If you look at typical structural alloys that are used for, let's say, aerospace castings, you will find iron level limits of 0.06 or sometimes even lower. Very common because aerospace castings are typically made with precision sand, which means very low freezing rate. So it takes very long to solidify, and the iron has a long time to form out these nasty needles. If you look at wheels or suspension parts, typically you would use an A356.2 as starting material. That means a primary alloy with 0.12 max iron. 0.15 the typical in the part, while in die casting with a high freezing rate, as mentioned, we can go up to 0.25%. So the typical candidates here are, I think everybody has heard about Silicon 36, the most common alloy in Oral 2 or 3 used by BDW, now Cosma. Oral 5S, another one. Then the Mercalloy, used by Mercumarine and more also by others. Castacil 36, W3, that's actually the Ryobi name. I think Ryobi was the one who made that very popular in North America, and now people recognize that as well. It's a Japanese alloy, but basically in the same family. These all have excellent castability, they're heat treatable, and they are the most commonly used alloy family. You see you have a wide variety of alloys and they're easily commercially available. The other one, more problematic alloy family, is aluminum plus some magnesium plus a little bit of silicon. The most famous candidate here is the Maximal 59. I heard it's actually not easy to get that alloy in North America, and it's becoming less and less popular even in Europe. It was developed because it has really excellent properties as cast or in a T5, so just artificial aging temper, but it's very difficult to cast, and really it just eats your dies. If you think of typical die casting alloys with an A380, 383, your dies last 150 or 200,000 shots. If you take these almost primary type structural alloys, the aluminum silicon family will let your dies last for maybe 80,000 to 100,000 shots. And with the aluminum magnesium silicon family, your die life goes down to, if you're lucky, about 40,000 shots. So there you see another big problem, apart from the problematic fact that these alloys also require beryllium, which is not easy to handle. They are susceptible for hot tearing and stress corrosion cracking. So therefore, let's focus on the aluminum silicon alloy family. Here the silicon is used to promote fluidity and ultimately castability. Magnesium at the low level is added to impart strength, forming so-called the mag silicide hardening Mg2Si particles. Iron helps reduce die soldering, but we know it negatively impacts ductility. The manganese is used to beat the die soldering. Usually it's also used to correct the iron phase. Titanium used as a grain refiner. Copper simply kept low because in those low levels it's not used as a strengthening element like in other alloys. It really is just a problem for corrosion resistance. And strontium, as mentioned before, is used for modifying the eutectic silicon, or in higher levels in the mercalloys to beat die soldering. So here's a picture of what the iron actually does. Both of them are 380 die castings, and we can see here in a 2D picture you will see it as needle-like structures. In 3D it's actually platelets, and they can be so nasty and go through your part that they actually cause it to crack. But at least they will block the feeding path and ruin your ductility. Now it was found back in the 90s in Europe that manganese is ideal for replacing this iron. So the first structural alloy available back in the 90s was the so-called silicon 36, still around, still used very often. And back then it was found that actually if you go up to 0.8 or even 1% of manganese addition, it doesn't really do much to your properties. It actually just improves your properties. Now we have seen before the sludge factor is 1 times iron plus 2 times manganese. So the more manganese I have in there, the more sensitive my alloy will become to sludge particle creation. So therefore is clearly the objective, and that was one objective, for example, why then the Oral 2 alloy works with a slightly higher iron content, which was found does not harm the properties. It works with 0.2, sometimes even 0.25, and then lowered the manganese content to only 0.4, 0.5%. And lately then Ray Donoghue from Mercury Marine said, well, actually the ideal point would be an 0.3% manganese content. This is where we usually see the peak in properties. Plus 0.3 is even better than 0.4, 0.5 in terms of sludge particle formation. But at that level, even with a 0.25 iron, an additional mechanism is needed to beat the die soldering, and therefore Mercury Marine has added the strontium, which was proven to help reduce the die soldering. Now if we look at what silicon and magnesium do, the main elements in this alloy family, we can clearly see the more silicon I add, well, the better my fluidity will be, but unfortunately the lower my ductility will be. but the higher my strength will be. Now, you won't determine your silicon level based on the strength and ductility you want to get. That might be taken into account, but mainly you want to determine the silicon level looking at the castability and fluidity in the alloy that you will need, and then adjust it with a magnesium content. And you see the blue line is 0 magnesium, and then I add magnesium, and the more magnesium I add, the more max silicide hardening I will get, which means the lower my ductility will be, but the higher my strength. Now, I have this plot here only until 0.2, but you can just imagine it goes on like this up to 0.6%. After that, you do not get more strengthening. So if we just have a look at, and I'm using the example of the Merkalois here because they're probably the least known of that series, because most publications were really made on the silicon and the oral alloys. But we have about the same principle. So we see in the 362 type, we have 11% silicon for highest fluidity. We use the 0.3% manganese, here a relatively high mag level, so we get higher strength, and the high strontium addition. And now we just play with the temper here. This is F temper, so S cast coming out of the die, and here at T6, full solution heat treated and artificially aged. And we can see the property packages easily meet and exceed the property requirements that we have seen at the beginning of the presentation. Now, of course, we can work more with this, and here we take the example of the 367 alloys, lower silicon, so we get actually higher ductility, but in this case we use first the high magnesium variant. So we start off with a pretty strong material, and as cast is more, the more we age it, usually we increase the strength at the cost of ductility. If we solutionize it, we will get to high ductility, and then the more we age it, we lose ductility and gain strength until we come to a point that we call the peak aging. And at that point, I have reached the top, and after that, I will overage it, and then it's no longer a T6. We actually call it then a T7. Which means then the stabilized position where it actually gets softer again, and we win back ductility. If we look at the 368, so again 9% silicon, manganese, same, lower magnesium, and we see higher elongation as cast, and we can boost the package even more by going into a T6. So ultimately, what you want to take away is the chemistry and the heat treatment can be tuned to meet a wide variety of property packages. So if you are actually specifying a part, you really don't want to specify a specific alloy and temper. What you really want to specify is the properties that you want, the exact requirements on the part, and then together with the die caster you can exactly define what are the process parameter and what alloy do I want to use, and then which temper do I want to use. Static mechanical properties taken in a low-speed tensile test, as mentioned before, can be quite problematic. Here, these were tests conducted in Europe by Pecheny, actually more than 10 years ago, and they said, well, let's compare it in real crush tests or crash tests, and they had alloys with relatively similar static mechanical properties, but then if you crash them and you compare T7, as mentioned before, solution heat treated and overaged, and F condition just as cast, you will see the result is the heat-treated parts survived the crash test. They were damaged, but still intact, while the S-cast parts they were really scattered into many different parts. So therefore, for safety critical crash relevant parts, it continues to be important that we develop proper heat treatment recipes that include at least partial solutionizing, and as I mentioned before, the quenching after the solution treatment is very critical for our tolerances, and you can see the difference here. If we water quench such a part, thin-walled, large surface, it will just warp like hell, and if we precision air quench, we can keep very tight tolerances. Now the beauty of the high freezing rate in die casting, as we mentioned before, is not only the very fine grain structure that we get, but that also helps that we can really shorten the solution temperature. And Ray Donoghue wrote a very good paper on that subject, saying that in high pressure die cast parts you can actually reduce this holding time on the solution temperature to below 20 minutes. And that almost doesn't give blistering the time to form out. So he has done a lot of work in this area, but again, I don't want to go into too many details. If you're interested, I can send you the full paper, or we can have a separate discussion on heat treatment. I have a full training course actually just on that subject. So with this, we have about 15 minutes left, and let's get into products and services that we offer, and then go into the summary and at least have a few minutes for questions and answers. So what Visi-Trak offers is per die casting machine, of course, all the process monitoring equipment that we described before, process control systems, the thermal monitoring, the total thermal vision system, any specifications supplied in order to make structural die casting, whether it's in metal treatment, alloy, heat treatment, and then all the way to production startup support and additional support on demand. So the services really are starting with alloy and process selection, optimization, sourcing, what is the ideal chemical composition of the alloy, guidelines for melting, melt treatment and transfer, and then the die casting process, improvement, optimization, etc. Casting simulation and optimization, the heat treatment for minimum distortion, temperatures, times, quenching, etc. Engineering support, die casting machine setup, heat treatment process, melting, project management, and all of that with a lot of training for engineers, operators, managers, and actually all the way to salespeople. And I've done that with a die caster that I actually gave training to the salespeople, so they were able to sell to their customers the advantages of well, offering high integrity die castings. So with that, we come to the summary. Traditional die casting processes, as we have seen, had difficulty achieving high integrity or low porosity castings, so therefore they were unsuitable for structural applications. The alloys rely on high levels of iron to beat die soldering, and iron, as we have seen, really destroys the mechanical properties, especially elongation. But new casting processes and applying proper process control, vacuum, die design, etc., and new alloys allow the production of castings with high quality and mechanical properties that are heat treatable, weldable, crash worthy, etc. And the inherent advantages of die casting, like the high freezing rate, thin walls, high precision, can now be used to produce high quality structural die castings at competitive costs in North America. So with this, I come to the end of my presentation, and let's have a look at whether we got questions so far. Jack, I have not followed any questions. Have we received questions already?
I don't see any online.
The only was whether there was a copy of this presentation available.
And we already clarified, yes, we will make a copy of the presentation available to whomever wants it. So, but can we unmute so that someone could ask?
Yeah.
I have one question.
Martin would have to do that.
Martin, can you unmute everyone else so if someone has a specific question they can answer?
Okay. Well, there was one question: what is typical heat treatment schedule, temperatures, and times for solution treatment and aging T6 for silicon? And is specialized furnaces required to keep up with production rate of the die casting machine? Okay. Well, to answer the first question, well, you need a special furnace for the heat treatment insofar as you want to optimize it with precision air quench. So you don't necessarily want to go to the full typical 520 to 540 degrees Celsius for 4 hours, because that's what you find in the handbook. You don't need this as explained with a high freezing rate. Very typical, you will be able to use just 490 degrees C, whether it's for an hour or even less. Again, I can send Ray Donohue's paper on that subject. Very important, it needs to be followed by precision air quench and then artificial aging, and that depends exactly on where on the aging curve you want to be. So, and you can get there either by longer aging times or higher aging temperatures. But that depends which property package you want to get to. I think it's a separate question for silicon 36. Are specialized furnaces required to keep up with the production rate of the die casting machine? Well, you want to have a separate furnace for this, because if you think about it, your A380 that you typically cast contains about 3% copper. Now, if you want to use silicon 36, the copper maximum for corrosion resistance is 0.03. So you have 100 times more copper typically in your furnace than you would want when you cast silicon 36. So really, I mean, either you would need to do a fresh furnace lining, or you need to do a lot of cleaning and furnace washes to get that copper level low. So I would recommend definitely have a separate furnace, a separate stream for the primary alloys that you use. Keeping up with the production rate of the machine is typically not a problem, because I mean, as we've seen, these parts are thin-walled. They are not massive. It's easy for any dosing furnace to handle these parts. It's not like engine blocks where you have a lot of metal going in and a lot of metal being pushed through. What is meant by precision quenching? Precision quenching in this case means, actually I could go back to that slide that was not far back. Here we have this. In order to avoid warping of the part, distortion of the part, you want to come out of solution and quench it at a certain cooling rate that you want to keep constant all the way down, and you want to apply precision air. So you want to blow air onto the parts, not quench them in water so they actually get quenched from the bottom to the top, for example. That is meant by precision air quenching in this case. I do not, the question is, do you see this process being done for brake parts in the automotive industry? I don't know which brake parts you're talking about. I know there are squeeze cast brake parts, but they're kind of a different animal here. Whenever you need these type of properties, you would use that type of process, and you can use it for all sorts of components. I mean, I've seen seatbelt retractor bodies that have to withstand the. It's almost like an airbag type explosion that happens inside the retractor body and then pulls the seatbelt back. And I've seen those seatbelt retractor bodies being made out of the same alloys and processes, for example. So yes, you can use it pretty much anywhere where you need these properties, but I am not aware of a specific braking part application. Jack, we have here one question. Does Visi-Trak offer a system to monitor humidity level in the die?
We have not had that request to date. You know, if, depending on the type of sensor, of course, if we got an analog signal level that was proportional to humidity levels, then yes, we could measure it, but we have not done it to date.
Yeah. Oh gosh, explain the mechanics setup for precision air cooling. For example, would jet air cooling be used? You would have simple fans, but set up in a certain way. I think the person who sent the questions on the precision air quenching or air cooling could just email me, and then we can exchange a couple of emails on that subject. I've been working, for example, with Canon in Niagara Falls up in Canada with their precision air quench systems, and they were used at Contact initially. That furnace, I think, went to Tesla in the meantime, but Albany, Chicago, Shiloh has the same system. It's not rocket science. They have this available, and I'm sure they could easily send you an information package on it. What equipment are available to inspect the metal properties? Now that depends where exactly. I think here quality of the furnace. If you want to inspect the metal quality, I mean, first of all, you want a spectrometer to check the chemistry. Then there are different equipment packages available to check the cleanliness of the metal. The easiest one is hydrogen content. For example, Foseco has what they call the ALSPEC H I guess for hydrogen. that's a real-time measuring system that you just really put into your melt, and it tells you how much hydrogen content you still have. You can actually link it when you buy their degasser, and it would then degas until you get to a certain hydrogen level. They're not the only ones who have things like that. There is a Japanese version, it's called the Voltcester, I believe, which also measures hydrogen content and then also cleanliness of the metal. If you just want to measure the cleanliness of the metal in the furnace, a very cheap and easy and quick way is the so-called K-mold. It's a little bit like casting like a tablet of chocolate, you know, where you break then the single parts away, and you can then visually inspect the break surface and see if you can easily see inclusions or porosity there, or what you can see there. It's of course very subjective. It's not an objective way to calculate or analyze the quality of your melt, but it's definitely better than nothing. And Japanese companies very often require that even from their metal supplier. So that's an easy and quick way to check the quality of the metal. If the question was more referred to inspecting metal properties in the part, there of course that totally depends on what you're looking for. Very typical, of course, is the tensile test. Everybody does a tensile test. There are standards how to cut a tensile sample and then how to test it. The problem, of course, as explained before, is it's a slow-moving process, so it does not exactly tell you how the metal will behave or the part will behave in a fast-speed test. And it's unidimensional, so it's just tensile properties. I have seen different tensile specimens being developed that will actually deform. They have certain shapes that will then unfold and deform in a three-dimensional way when they are pulled. Or, as mentioned in the beginning, it is becoming more and more common to actually have a bending test. So like in sheet metal, you basically take a sample out and then put it either between rolls or in there is actually a standard how to bend it to a certain angle with a certain radius, and that way you see actually how the metal or the part behaves in a three-dimensional deformation. I hope that answered the question. And then, of course, you can do whatever test would be representative for what you want to do with the parts. So very often, if you want to weld the parts, well, then you might want to have a welding robot or some sort of installation that allows you to weld on the part, so you can check whether weldability is given. Or if you rivet the parts, then take samples and actually punch a couple of self-piercing rivets into them and see if you can get cracks.
Okay, it's 5 o'clock, Martin. I think really thank you for your very outstanding presentation, and be happy to, if anyone wants to email and request a copy of the webinar, we'll be happy to send it to you as soon as it's available. And if you have any further questions of us here at Visi-Trak, please email me, or you can email Martin directly for anything you have further questions from him. And we appreciate your taking the time to join us today. Thank you very much.
Okay, thank you.
Thank you, Martin, very much.